Welcome to our YouTube channel. Today we are discussing about the applications of Fresnel Biprism experiment. Very first application is determination of the wavelength of monochromatic light. Our aim is to find out the wavelength of monochromatic light using Fresnel Biprism experiment. We are starting with a formula from Young's double slit experiment, that was lambda is equal to beta d upon capital D, where beta was the fringe width, small d is the slit width, capital D is the separation between slit and the screen. Now let us suppose experimentally we can measure all these values, beta, small d, capital D, and then substitute these values in the formula for lambda. That means we can experimentally determine the value of lambda. So this will be our flow chart. Step by step we will determine beta using Fresnel Biprism, small d using Fresnel Biprism, capital D using Fresnel Biprism, then substitute all these values in the formula for lambda and we can calculate lambda. Let's start with the step number 1. Measure beta using Fresnel Biprism experiment. First I set the apparatus. I have taken an optical bench, means a bench that is provided with a scale. Now I have placed 3 uprights. Uprights means stands. First upright carrying the slit, second upright carrying the biprism, and third upright carrying the eyepiece fitted with micrometer. This red color is a source of light. Then now what I am doing, I will illuminate the slit with the help of source. That means a fringe pattern is obtained on the eyepiece with the help of Fresnel Biprism. Now this eyepiece is fitted with micrometer. That means I can set at any particular fringe. Suppose I set the micrometer on 1th fringe and I have noted the position of 1th fringe. Now I rotate this eyepiece and set the eyepiece on 11th fringe. And again note the reading of the 11th fringe, that means the position of 11th fringe with the help of micrometer. Now I have the position of 1th fringe A1, 11th fringe A11. How many fringes cross the field of view? 1 to 11 means 10 fringes cross the field of view. That means distance between 1th and 11th fringes A11 minus A1 divided by, this is the width of 11 fringes. If I divide this width of 11 fringes by the number of fringes, that will be the width of one fringe. That means A11 minus A1 divided by 11 minus 1 is equal to width of one fringe. Is it clear? Means I have measured the width of 10 fringes, then divide that width by the number 10. This is the width of one fringe. Fringe width. Now if I generalize this formula, I may write it as an small n, an plus capital N, position of n plus nth fringe, and width of n fringes is an plus n minus an. Width of one fringes, divide this width by capital N. So the formula is beta is equal to x by n, that is distance moved by the micrometer, divided by number of fringes that cross the field of view. Is it clear? Simple formula is find out the width of n fringes, divide this by n, that will be the width of one fringe. Done. So we have first parameter beta. Step number 2, second parameter capital D. Separation between slit and the screen. You have the uprights. Note the position of upright containing the slit. Note down. Note the position of the upright containing the eyepiece. Note down. Find out the separation between them. The separation between position of eyepiece and position of slit is the capital D. Then, so you have two parameters, beta and capital D. Now step number 3, that is small d. Now we will measure small d using displacement method. So our experiment is Fresnel Biprism experiment. If you remember the last video, we have source and then we proved that the source produces two coherent sources of light. These two coherent sources of light are S1 and S2, two virtual coherent sources of light. Virtual sources. That means I have to focus these virtual sources on the screen so that I can measure the separation between these two virtual sources. Suppose S1 and S2 is small d. Now I have to use a focusing lens to focus this S1, S2 on the screen. Focusing lens is convex lens. Now I am using a convex lens to focus the source S1, S2 on the screen. Suppose distance of convex lens from the object is u is equal to small m, and from the screen is v is equal to small n. Now S1, S2 is small d, and suppose the height of image is small d1. Now I apply the lens formula here. Height of image divided by height of object is equal to distance of image divided by distance of object. Then that means d1 by small d is equal to v by u. V is small n, u is equal to small n. Label it as equation number 1. Now case number 2. Now displace the convex lens such that distance of convex lens from the object is small n and distance of lens from the image is small m. The height of object is small d and height of image is d2. Again apply the lens formula. That means d2 by small d is equal to v by u. Now v became small m, u became small n. Label this as equation number 2. So because we have displaced the lens, that's why this method is named as displacement method. Now rest is only mathematics. You have equation number 1 and equation number 2. In the next step, we will apply equation 1 with equation number 2. So if you multiply 1 and 2, it would be d1 by d2 upon d square is equal to 1. That means d1 by d2 is equal to d square, and small d comes out to be the square root of d1 d2. Focus on this mathematics. It would be clear to you that small d is equal to the square root of d1 and d2. d1 is measurable, d2 is measurable experimentally. On substituting these experimental values, you can find out the experimental value of small d. Thus, up to now, you have determined all the 3 parameters: beta, capital D, small d. If you substitute all these values in the formula for lambda, you can easily determine lambda. that is the wavelength of monochromatic light. Next is the measurement of thickness of thin transparent sheet. Suppose you are doing Fresnel Biprism experiment and a thin film of given refractive index is given to you. Now your aim is to find out the thickness of this thin transparent sheet. How would you perform this? Let us start the experiment of Fresnel Biprism without any thin film. So what would be the position of central maxima? Point O. Why point O? Because point O is equidistant from S1 and S2. Because the path difference between S1O and S2O is 0. That's why O was the position of central maxima. Now, second step. Suppose a thin film of refractive index mu and thickness T is introduced in the path of one of the interfering beams. What would happen? The beam will be deviated from its path. How the beam will be deviated? Now the beam will not reach S1O. Beam will travel as S1P. So the path of the beam is deviated from S1O to S1P. Now the fringe is formed at the point P instead of O. What is the shift? Shift in the position of the fringe. That is OP, small x. Let us suppose the distance of slit and the screen is capital D. Now, what's the effect of introducing thin film? The effect is central fringe gets shifted to a position which was originally occupied by the nth bright fringe. Because P was the position of nth bright fringe when no thin film was present. And now P is a position of central maxima. In nutshell, I may conclude that when a thin film is present in the path of one of the interfering beams, the central maxima is that point P, which was originally the position of nth bright fringe when no film was present. Because now I am saying P is the central maxima. I may use the word central maxima only if the optical path of S1P is equal to optical path S2P. Only then I can name P as a central maxima. Now let's check what's the optical path S1P. Optical path is actual path into the refractive index of medium. So now calculate the optical path S1P. S1P is a path that is travelled in air and thin film both. How much path is travelled in air? S1P minus T path is travelled in air, and small t path is travelled in the refractive index mu. So the optical path S1P is equal to S1P minus small t into refractive index of air plus T into refractive index of thin film T, that is mu. So we can say that path S1P P, optical path S1P is equal to S1P minus small t into 1, that is the refractive index of air, plus small t into mu. Then now S2P optical path. S2P path is totally in the air, so S2P into 1, refractive index of air. This is the optical path S2P. Now from this equation we have S2P minus S1P is equal to mu minus 1 into t. Keep one parameter on left hand side and all other parameters on the right hand side. We can calculate the value of S2P minus S1P is equal to mu minus 1 into t. Label this as equation number 1. Now if you remember, what was P when no film was present? P was the position of nth bright fringe, that is part difference S2P minus S1P in that case was xd by capital D. Part difference formula is xd by capital D. Now if we equate equation number 1 and equation number 2, we will be having mu minus 1 into t is equal to xd by capital D. From here small t comes out to be xd by capital D divided by mu minus 1. Done. So this is the expression for the thickness of a thin film using Fresnel Biprism experiment. Here small x is the distance of nth fringe, means point P from the point O. Small d is the slit width, capital D separation between slit and the screen, mu is the refractive index of the film. So you can measure small t. Thickness in terms of beta and lambda. You have the formula for beta is equal to lambda d upon small d. From here small d upon capital D comes out to be lambda upon beta. If you substitute this value of small d upon capital D in the above formula, that means small t comes out to be x lambda upon beta mu minus 1. That's it. So this is the formula for t in terms of beta and lambda. So this was the applications of Fresnel Biprism experiment. Thanks. If you like the video, don't forget to like, share and subscribe the channel. Thank you so much.